Okay, in this video we are going to combine momentum and energy. These problems are interesting to solve, trying to figure out when are you supposed to use momentum versus when are you supposed to use energy. And the one that's shown is a very popular one called the ballistic pendulum. So let's first take a look at what is really happening with the ballistic pendulum.
Okay, here's a popular situation that involves both momentum and energy. It's called the ballistic pendulum. We have something very similar to a projectile launcher that we used for projectile motion right here. Has three different settings where a spring is compressed. Whenever that lever's flipped, it'll fire the projectile, but it's going to stick inside this block. There's an opening right here for the projectile to stick into. And since it is a collision, it's going to stick together and continue to move. However, there's going to be a change in the energy because this is stuck like a pendulum, and it's going to swing up to a certain height. All right, so you can see that the marble is stuck inside the block. We have a measurement of the angle that this rose up into the air, and we therefore can figure out what the change in height is.
Just in slow motion. So you can see clearly how that worked out. Okay. So we're going to write up a proof of this situation using the given variables. All right, so we will only have little m, v naught, big M, the combination, and let's calculate how high it's going to go. Okay, first we have to think about when the collision occurs and when we have to use momentum versus when the change in energy occurs. So in this situation, the bullet is colliding with the block, and it's colliding along that plane right there. Now, once this bullet sticks into this block, it's going to try to continue moving forward. However, it's attached, and as it tries to move forward, it's going to have to move upwards. So the change in energy occurs after the bullet sticks into the block, and the block begins to move forward, the block-bullet combination. And as it tries to move forward, the energy is then changed to potential. So the first thing, in order to get to the end part of the height, we're going to have to solve a collision problem between the bullet and the block. Now, concept of momentum is that the initial momentum has to equal the final momentum. And just remember that that little apostrophe stands for prime or final. So we look at the system before the collision, and the only thing that has momentum is the little bullet. At the end, we have a bullet and block system. Now that is the sticky type of situation, so that the total mass of the block plus the bullet is going to be moving with that speed. So that's our momentum statement. In order to figure out the height, we need to know how fast the bullet and the block are going to be moving in that direction after the collision, because the kinetic energy that is gained by the collision is going to have to change to potential. So what do we need? We need to find V prime. So we're going to manipulate this for V prime. And now we're going to have to use that into our energy expression. So for the energy, the initial energy has to equal the final energy. And the energy at this point, right after the collision, the only form of energy, if we make this line our zero line, is kinetic. So we have 1/2 the mass that is moving times the velocity squared. And that is going to be changed to MGH. To all potential when it stops at its highest point. Now, one nice thing in the energy expression is that as long as there is no spring involved, the masses usually cancel out. Now, don't hold me 100% to that, but from experience I've noticed that as long as there's no spring, those masses will cancel out. All right, I'm going to move some stuff around here. We still need that velocity value, and we're going to solve for h here. So h is going to be equal to v prime squared over 2g. However, we need to put the given information back into there, just like they would ask on an AP problem. All right, so we're going to have mv naught over the total mass, and that's v prime squared all over 2g. Now, this is not the nicest looking proof here. So if this was an AP exam, they would probably give us more information such that maybe the big block is 4 times greater than the mass of the bullet. And then we can substitute that stuff into here. So we'd have little m times v naught, and that's all squared. And here we'd have 4m plus little m, and over the 2g. So here the m's would all cancel, and we would end up with v naught squared over 5 squared over 2g, and it can simplify down as v naught squared, 5 squared is 25. That drops down at the bottom over 50g. We can do this with any type of energy transformation problem. I found this one, maybe we can work through. Actually involves a lot. All right, so we have a block here, gives us the masses of these two blocks. It is released at this height, slides down, reaches its maximum kinetic right before the collision. When they collide, it says that they stick together, all right, and then it slides across this surface that has friction, and the friction is listed here, and then it ends up in contact with the spring, so that with the spring constant here, and we're trying to figure out how far does the spring compress. So let's work this out. First, we have an energy problem. So just from the block moving from its highest position down to its lowest position, that's just the transfer of energy. Now, in order to do the momentum portion, we would have to know the velocity of block A. So we can't just start with the block at the highest point. So the first part of this problem is going to be MA. So it's our energy expression, the initial energy at the height of 6. And we're going to change that into its maximum kinetic. Whenever it gets down to x equals 0, right before the collision. And this is just a simple energy problem that we've done plenty of times. And if you follow through with the work, we'll see that we get a speed of 10.8 meters per second. And that's how fast block A strikes block B. So now we move on to the next step in the sequence of events, which is the momentum collision problem. So before the collision, block A has momentum, block B does not. All right, so we have the mass of A moving with the velocity of A before the collision. And that's going to equal, it says that they stick together, so the total mass, ma plus mb, moving at the new speed afterwards. Because it's the speed that it's moving after the collision that is going to actually affect the spring compression. But there's still another energy problem that goes along in between there. All right, so solving for v prime, which is going to be the speed that both blocks are going to be moving with after the collision. Do the manipulation first, and then plug in the numbers. And we'll get 7.2. Now, conceptually, that should make sense. If I had two blocks that were the same mass colliding and sticking together, so if block B was 10 and the initial speed of block A was 10, after they stick together, it would cut the velocity in half. So that would be if it was the same mass. Now, since block A is heavier, it's going to have a speed greater than half. So greater than half the original speed. If block B was heavier than block A, it would have a speed less than half. Now, where are we in this problem? All right. We know how fast both blocks are going to be sliding across the friction surface here. So we don't need this so much right now, but it's now an energy problem. So at the start here, all of the energy is kinetic. So 1/2 the total mass times the speed squared. Okay, and then at the end, right here, it's going to lose a certain amount of that kinetic energy and turn it into heat. Now, we can actually figure out what that value would be, but we would then have to add another part onto our problem. Because once it reaches this end, and it'll reach there with a much less kinetic energy, all the kinetic energy at this point would then be turned into spring energy. So even though there is no friction once it hits the spring, we can combine both the gain of the spring energy and the loss of friction into the final energy here. All right? So we know we're going to end up all with spring. But we lost energy due to friction. And I'm adding the friction to this side because we need both the kinetic over here and the total energy over here to be equal. So if the spring energy is going to be less than this, you have to add whatever energy was removed to the right-hand side or subtracted from the left-hand side. So with friction, we know that it's going to be mu mg. So we have a lot of numbers we have to write down. So I'm going to switch back to variables, shorten it all up. All right, so that's 1/2 the combined mass times that velocity afterwards squared. All right, there. And just so you can see in the friction equation, mu mgd, we need the total mass there. Now you can see, because there's a spring, the masses don't cancel. So we end up with this long equation just to solve for the x that we need. So manipulate that for x. And you get this mess. And if we plug in all our numbers, which I will, we'll get our final answer. And just a comment here. That distance is the distance of 12 meters that the block slid over the frictional surface. And remember the coefficients up there. And once you plug everything in, and make sure you square root it, you should get 1.23 meters. And that's just an example of energy and collisions being used together that just had two energy parts instead of one, just like the ballistic pendulum. And you can always end up solving for something at the beginning. So if we had how far the spring compressed, we can work backwards and figure out how high the block must start in order for that situation to occur. Same thing with the ballistic pendulum. We can figure out how fast the bullet had to be traveling in order to raise it up to a certain height. Hopefully these two examples were enough. On this app, it's difficult for me to move my work around and keep it in an orderly fashion. So hopefully you were able to do that while following along, and you should be able to tackle a few more problems on that website now.